Hey, good afternoon. Awesome to be, I guess, the last presenters, which is always very interesting, but I hope you guys are having a good time here at SIGGRAPH. Before getting started, we want to definitely say thank you to Side Effects for the opportunity to speak here. We have been using Houdini for a long time. We're definitely geeks and love the toolkit, but I think one of the things that's most exciting about being here is actually being amongst other users and also getting to meet up with some of the people who have championed sort of the dissemination of Houdini learning content that we've been able to use to sort of accelerate learnings. And I hope this will provide a little bit of learning for you as well. So to get started, let's just kind of like dive right into it. In recent years, there has been a pivotal transformation in the discovery, understanding, and usage of materials, thanks to computational modeling and simulation advancements. This transformation, paired with inventive geometric design as well as 3D printing, has really opened up a whole new world and a new class of materials that are typically referred to as metamaterials. There's been a few talks the past few days that have dealt with similar subject matter, so maybe you've heard of this. Our talk today is going to introduce current work in progress at the studio toward building a scalable pipeline in Houdini to accelerate the design, development, and analysis of these so-called metamaterials, specifically for advanced product design applications. My name is Ronnie. I've been working for more than 20 years in computational design and 3D printing. I have a background in architecture and product design, and early in my career, I developed a deep passion for materials, manufacturing, and coding.
And I'm Evan. I'm also trained as an architect, and I've spent about 20 years or so in computational design and systems thinking. And have spent a really good amount of that time researching and exploring biomimicry and material systems for performance-oriented design. And we're here from ModeLab. We're a sustainable innovation company helping brands bring new products to market using advanced design and manufacturing systems. Our work spans across multiple industries, from consumer product, manufacturing, medical, and automotive. And we focus much of our efforts on developing the digital tools and the techniques needed to make products real. And in today's talk about a new materials pipeline in Houdini, we'll touch on four kind of main areas. The first is we'll review our metamaterials pipeline, kind of where we currently are in our work. We'll talk about the modeling and visualization approach we're using and the automation tools that help things scale. We'll talk about how meshless FEA, finite element analysis, fits into our simulation and evaluation workflows. And finally, we'll talk about where we look to take our pipeline in the future. And so we live in a world of materials. Materials give substance to everything we see and everything we touch. And while humans are not the only species to create objects out of those materials, we're the only ones that look beyond a material's functional characteristics. We don't just make objects, we design them. And we incorporate both function and aesthetics into the things that we create. And so within this design process, material selection plays a really critical role. So traditionally, choosing the right materials involves kind of two main paths. On one side, there's technical design, engineering, and on the other side, industrial design. And with a wide array of materials that are available to us, engineers typically consider factors like performance limits and constraints, while industrial designers typically focus on desired appearance, the emotional connection you have to a product, etc. And the materials then that we specify, ultimately they're chosen from a library of known options. However, they live separately from the specific product applications they'll ultimately materialize. But over the last 5 years or so, advancements in additive manufacturing have really changed the landscape of materials. With additive manufacturing being a younger technology, there's still a gap to close regarding the development, the standardization, and the qualification of materials used within that technology. And while there are fewer materials to choose from, there are some really incredible opportunities to design them from the bottom up. And so in a typical product design process, a product's developed, a material is then selected, and then it's applied to the product. And in many cases, the material or the materials chosen, they do have an influence on the product itself. But this is really relative, to the materials that are available for selection. But what if materials could be designed with a specific product in mind? And what if we could design materials specifically for a product's performance and its aesthetic requirements? What would these materials look like? How would they behave? How would they shape and be shaped by those products? And really a new class of materials has emerged that uses geometric design to transform existing materials without chemical or molecular change. And these materials are called metamaterials. These metamaterials are materials that are designed with a specific internal structure to exhibit unique and desirable properties that aren't found in naturally occurring materials. And taking a conventional material and structuring it on the metascale in the form of a cell, as we saw in the last slide, allows us to build kind of structured metamaterials that are designed to move beyond the restrictions of conventional materials. And so at the micro scale, advanced functionality is designed into the structure of the material itself. The next level up at the mesoscale, interactions between units create regional behaviors, and then differentiated material characteristics occur there. And then finally, the metamaterial performs kind of holistically at the macro scale. And it's this interplay of hierarchies that makes metamaterials so unique. So really the key here is that those simple design changes that can happen at the local scale unlock some really complex behaviors at the global scale. And so if we now have this opportunity to design these new materials and the functional and aesthetic performance of materials through their structure, what activities are required and what does this look like? And so our pipeline addresses two primary requirements. On one side, the digital, and the other side, the physical metamaterials development. So in support of this, we have 5 key activities that need to be orchestrated. So first, we need a modeling environment that allows us to create, iterate, and generate material organizations. Then we need visualization that allows us to build the communication tools needed to collaborate across teams and evaluate material outcomes. We need simulation to bring engineering requirements and results directly into the design process so that different metamaterials can be tuned for performance. The creation of part files for additive manufacturing needs to be integrated into the overall design and development process to ensure that we're preventing any bottlenecking. And finally, the products that we interact with are physical, and therefore they need to perform in the physical world. So while digital simulation enables us to rapidly validate designs, physical testing helps us calibrate these analyses and get closer to performative solutions. And then in order to bridge between design and engineering, we leverage JSON files to provide the interoperability between Houdini and our external finite element analysis. So you can see here, kind of between modeling and visualization into simulation. From this simulation, external simulation, in order to initiate this external simulation, the JSON essentially initiates an analysis through an external FEA solver called intact simulation. And the results are then imported back into Houdini for evaluation. And so here in this video, we can see kind of this process in action. Here you can see a unit cell is being constructed and then placed into a map that creates a larger material organization. We then use, in a top network, we use wedging in order to generate multiple different options within our parameter space. we then are able to, so I'm trying to catch up with the video, we use ROP Mantra and our overlay text nodes for communication purposes, and then use Image Magic to compile all that so that we're able to now communicate the potential metamaterials and opportunities, both for ourselves, but also externally to other team members. From there, we can go into our simulation. So here we can see that there's a metamaterial that is selected for analysis. Within a simulation preparation HDA, we run a Python script that creates our JSON and all of our supporting geometry that's required. We then send that headlessly via the command line to initiate our FEA with intact simulation. After that runs, whoops, we have a, that's all right. We have a second HDA that then converts that file into a PLY, so it's readable back into Houdini. We can do the evaluation there. And so throughout this pipeline, there are kind of a multitude of data types that are created and passed throughout contexts and between internal and external processes. So Houdini provides us a really great opportunity to develop that those interoperability workflows, streamlining work across those multiple touch points. And so while this pipeline in its entirety is necessary to bring metamaterials design to life, today we're going to focus on a couple of key areas related to the digital materials development only. And so that's modeling and visualization, and then simulation and evaluation. But for those who are interested, we do have a couple of physical material samples that you're absolutely welcome to come and play with after our talk.
Cool. So I'm going to jump in to the more specific areas of Houdini that deal with modeling and visualization, so you can kind of understand in a very practical way kind of what are we doing and why in order to be able to support this kind of a pipeline. So the first thing to note is that Houdini, it's not like your typical kind of DCC. I like to think of it as like a pipeline in a box. It's more like an OS or an operating system for everything that you might need to do in film, VFX, etc. But also it just so happens to do the same for us in physical product creation, right? There's a lot of parity between the things that need to get done for film and VFX and product design. Under the hood, there are a number of really awesome technologies within Houdini, and one of those technologies is access to OpenVDB. We have a background in working with CAD. We're expert surface modelers, can build anything you can imagine, right? From footwear to automotive, etc. But the way that we build surfaces for tooling applications or conventional manufacturing is fundamentally different than when you're talking about additive manufacturing, right? It's a different technology of make, and it requires different ways of modeling in order to be able to work with it effectively. One of those technologies that we use is, again, OpenVDB, and the underlying concept behind OpenVDB is something called fields, and these are represented typically through voxel forms as something called a volume. So just a quick show of hands, how many of you are familiar with working with volumes and voxels in a modeling capacity? Okay, cool. So I'm going to not go too deep into this because I think we have experts in the room already, so that's great. But I think the key thing to note is that when you're talking about traditional CAD, you typically describe shape through an aggregate of curves, which then form surfaces, and those surfaces then come together to form a solid representation, right? Here in this world, we actually work more with understanding properties like density and where densities change in order to be able to derive shape, right? So it's a fundamentally different way to approach modeling, and it requires the use of a couple of really cool tools like volumes, VDBs, and for us, a heavy usage of VEX scripting through the volume wrangle, sometimes some stuff in the VOPs, volume VOPs, but primarily it's going to be through VEX. Why that's important and relevant is that when we're talking about metamaterials, there are many different types that you can work with. And the classification of metamaterials goes beyond the ones that we're actually going to show and talk about today, which is a subset called mechanical metamaterials. You can imagine in the world of physical product creation, specifically within consumer products, how things function mechanically is super important, right? So when we're dealing with setting up a system, a design system for working with metamaterials, we need a really fast way to be able to model the geometry, but we also need a really fast way to ship the tools to users who don't have the technical capacity to code these themselves, right? So we wrap a lot of our work up into digital assets. Here you're going to see 3 different digital assets, which represent 3 different metamaterial types. One on the left, my left-ish, the unit cell expression based allows you to type mathematical expressions in order to shape a surface. The second one, strut, you define links between nodes, and that then allows you to form a structure. And then the third one, shells, is that you're actually defining planes in order to be able to give shape to a metamaterial unit. Now, this is really important because of all the different types that there are, each one of them has very unique kind of performance characteristics. And so on the front end, we allow for a number of different visualization modalities in order to understand kind of what that cross section is through the actual form itself or unit type. And we also provide a number of different outputs, from volumetric data to mesh polygonal data to solid data as well, which is very important, again, when you're talking about physical products. You need to be able to output to multiple types, which can then be tested. Now, over here, you're going to also notice that the unit type within a metamaterial aggregates. And the way that it aggregates dictates the sort of organization and the structure of the overall material system, okay? Now, the units that we deal with are all modeled in voxels, right? And then the environment that we put them in is also made of voxels, right? So if you think about this as this cube here, that represents something we refer to as a cell map, okay? And you can see here in our procedural graph, the cell map is the very top level, right? So that dictates where a unit would be propagated. The second aspect of how this works is that we're using something called a weight map. And so essentially, if you're familiar with volumes, you can kind of think of it as fog, right? And in our case, the way that the fog is being used, or the density attribute is being used, is we're telling it to inform the characteristics of a particular material, be it through a parameter of some type, right? So you have a cell map that says where these units should be placed. You have a weight map that says how those materials can be tuned. And then you have an aggregate of the unit type. And if you notice here, you'll see that the parameterization of that unit is actually changing by way of the fog, right? And that's the sort of underlying kind of concept in how our modeling rig is set up. Now, looking into this a little bit further, one thing to note is that, although there are many different metamaterials that exist, there are a number of very related feature sets that you can use in order to be able to tune them. So that makes the underlying kind of architecture of how you go from a unit to an aggregate system really easy to kind of work with and design with. So here you're going to see a unit type. This is a beam and strut type, and you'll notice that you have the cell type, you have the cell size, and then you have the strut size. But anyone who works in sort of generative geometry and things like that will know that 3 parameters by themselves is already a significant design space to have to deal with whenever you're talking about trying to lead to discovery and sort of invention within the system. And so when we look at those different features, just say 3, working across all these different types, you can now imagine, you now have like 3 by an additional 1, right? So you have 3 by 4. And so the design space gets very large, very quick. So we're going to take a look at an example really quickly that looks at one particular cell family. These are all tetrahedron types. and looks at how that particular unit type can start to be kind of tuned using a couple of additional technologies within Houdini. So using this kind of volume-based modeling technique, right, we're able to quickly tune and prepare geometry for testing purposes. Now, when we set up tests for product design, we're typically designing an experiment, and that experiment sets, hey, this is what the objectives are, here are some of the criteria, here's a range of performance we're looking to validate for, in order to be able to then determine whether or not a particular structure performs in a way that is advantageous or not. Here you'll see that we're grading the strut, right, across this particular type. This is called a star tetrahedron. And we're holding the cell size consistent. So the strut size is being tuned between 0.42 and 1.12 millimeters across the domain. Now, that works pretty well if we're talking about a really simple DOE, or design of experiment. But when it comes to scaling that kind of a workflow, we really need to tap again into some other technologies that ship with Houdini. And one of the key technologies that we're kind of in love with is the task operators. How many, again, show of hands, are using TOPS or PDG in your workflows? Okay, awesome. Yeah, definitely an amazing technology. Would love to talk to you more about it afterwards. But we're using these TOPS to manage our material design workflows and efficiently distribute tasks is kind of the takeaway. This low-level access to Houdini's procedural dependency graph via the top network lets us specify the dependencies that exist between work items or metamaterial features, right? And how they contribute to the final kind of architected material output, okay? Now, we use rendering with Mantra. We're shifting to Karma and Solaris at the moment, but currently still kind of using Mantra. And that allows us to very quickly, kind of render output, build contact sheets with all of the parameters of our DOE, making it really simple for communication purposes and bringing people together to say, hey, this is really interesting here, here, or here. How did we get there? We can send that out to simulation. We can test that, and then we can recreate it really quickly. Combining that quick design loop with the ability to print something like this in 10 minutes allows you to go from digital to physical very, very quickly and with a high level of integration. And based on the discoveries, right, that we kind of make along the way, we begin to make design decisions and start tuning the differentiated structures. Understanding the differences between these metamaterials enables the creation of structures that are no longer homogeneous, but variegated throughout space. So some of the structures as well, from a strictly engineering or technical point of view, may be unintuitive in terms of why they would be relevant to a particular application. But because we have the ability to explore very broadly using TOPS and PDGs, and we can understand through communication tools what the benefits or trade-offs are, we can actually move into more of an unintuitive space where design loves to live, right, to lead to new discoveries in terms of the materials. So this deep understanding of materials and manufacturing is really a core element of our design process and design in general. Our goal by building this type of a pipeline is to provide a solid foundation of capabilities and technology alongside information and knowledge for teams around M&M to essentially support the exploration and development of advanced metamaterials or new material systems in the context of product design.
And so alongside this capability to create a large number of potential metamaterials, we also need the capability to analyze and evaluate their performance. And so while Houdini does have a large body of simulation tools, we have currently to date focused primarily on external engineering simulation tools. And here we're using Intact simulation. It's a meshless FEA solver from Intact Solutions, which differs from, let's say, more traditional FEA solvers where computational meshes need to be constructed. And that can be headlessly run via the Windows command line. interface. And just a quick thank you to the team at Intact for their support while we've been building this out. And so kind of walk through the simulation process a little bit here. So really this process takes advantage of a number of features that Houdini provides, moving across contexts, hooking into external software packages in convenient and really streamlined fashion. So first, an HDA is built to take prioritize metamaterial structures, build out the required simulation assets, and then run a finite element analysis externally. So that HDA uses Python to write the JSON that's required to compile all the design parameters, and then also prepares the VDB file to analyze, as well as all the load and restraint boundary conditions to run the analysis. This Python script also then opens the Windows command line interface, initiates the analysis scenario, passes the JSON file and the other required files to Intact. And then Intact simulation runs in the background and produces a VTU file, which allows us then to read analysis results, such as von Mises stresses or displacement values. Once that's run, we have another HDA, just kind of our visualization HDA, that is then used to convert that VTU file via the VTK library into a PLY, and that can then be read back into Houdini and visualized within our modeling environment. And so, in this context of simulation, we begin by exploring metamaterials by using wedging in the top network, in the top context, and that allows us to begin to open up the parameter space to begin understanding behaviors of differentiated materials. And so this initial analysis partly is done visually, and really the reason that we kind of start at this base level, it's really important to understand performance with a certain rigor. And so here we explore a single unit type with different beam dimensions as the start. But then once we understand kind of the outcomes from those initial analyses, we can then introduce additional parameter changes. And so here, for example, we're adding a y height as a parameter in order to explore the benefits or change in performance when materials are no longer orthotropic, which means where their properties are the same in all directions. But we can begin to explore them when they're isotropic, so they have material properties that are different in different directions, which does cause a big change in performance. So then again, leaning on the power of PDG in TOPS, we can continue to expand the breadth of our discovery process, and do that without any additional modeling work required. And then just by simply increasing the wedging count or by tuning the parameter space bounds, we can identify material organizations that look to be promising and generate a vast number of prospective opportunities, all within that clearly defined scope. And so within that space, we can then cut a cross-section through in order to prioritize a set of metamaterials for simulation, analysis, and evaluation. And in this case, we're looking to understand the behavior of vastly differentiated structures. So these are different cell types, different beam thicknesses, and different distributions. And here we can see the results of those 4 prioritized metamaterials after analysis, running through the workflow that was previously described. And what's really fascinating here and really supports kind of the need for this type of study is that the results are often not what we'd expect intuitively. And even without a great deal of materials or engineering knowledge, we are not engineers, we can see that structures with large beam sizes don't necessarily have the least displacement, and that is typically what, without any other information, you may expect. Of course, at the same time, geometry plays a major role in performance. And so what we begin to understand here pretty quickly is that simulation and analysis really unlock new levels of discovery when we're working with metamaterials. And really what we see is not what we expect.
So talking a little bit about future developments, as I'd mentioned before, our background is we've been using Houdini for a really long time, and we also use CAD tools and other tools. what we want to do is sort of eat all the other tools and use Houdini to sort of provide that infrastructure to kind of remove more and more tools from the stack. But at the same time, we want to close the loop between our analysis and simulation, evaluation capabilities, and design. So in this presentation, we primarily focused on how the design and development of metamaterials can occur from known types, right? But of course, that's not where you end, right? What we're looking for is the discovery of new types, right? So by closing the loop and integrating new technologies into the pipeline, we can actually start to unlock some new capabilities that are currently outside of what's possible with the tool sets that we are currently using. So closing the material design loop is one of the key things that we're focused on. And if any of you are interested in product design or 3D printing or the future of kind of material development for physical product creation, let us know, because we definitely believe that this type of a pipeline, this type of work requires an interdisciplinary approach, and there's a lot to be learned from each other. So to wrap it up, some of the key learnings we wanted to share was that even starting with the known types of metamaterials that are well documented, the parameter space that they exist within, right, provides a sort of an expansive world to explore. Exploring that world with conventional tools and conventional ways leaves a whole lot on the table, right? And new tools are needed in order to kind of to explore that more effectively. But at the same time, striking a balance between creativity and kind of computability is key, right? So we need speed, yes, but we also need design, right? And design isn't an objective thing, right? So we have to support sort of advanced creativity and the needs of designers while also being able to meet the requirements of technical product creation and the expectations of engineers, right? The last thing is that interoperability is a really great way to unlock discovery. Again, Houdini, it provides such a rich ecosystem of tools, but even within those tools, being able to then integrate external tools to be able to enhance the workflow is, not a heavy lift, and that's an exciting thing for, somebody who's working in innovation and wanting to kind of move really fast, right? So interoperability where you can integrate is definitely something that can kind of lead to faster discovery in the process. So we're going to kind of end it there. It's a short one. We only had 30 minutes, but wanted to thank everybody for your time today. And I think we actually have a few minutes for questions reserved here at the end. So if anybody has any questions, we're happy to answer them now or stick around afterwards and we can get together.
Thanks.
Thank you.
Questions, anybody?
To what extent does visual aesthetic play a role when you're, like, for example, choosing a certain unit structure? Would you say it's like mostly functional?
Well, it's a great question. It's not only functional. What's kind of surprising is that if we look at it from a functional criteria or objective alone, you'll very quickly meet the requirement. So it leaves a tremendous space for aesthetics. And I think that product design, as Evan had mentioned, being the convergence of technical, right, and creative, is that space where you strike a balance between the visual propensity of a particular system and its engineering capacity, right? So yeah, we're both designers and we're pretty hardcore about design. So most certainly aesthetics plays a huge role.
Yeah, and I think that, when I was mentioning kind of the process that we're taking currently as to what we prioritize to run simulation on, there is that first kind of aesthetic check, right? Like, does it look good? Does it work, from a design perspective? Otherwise, we could test millions and millions of structures. But if we're going to only get performance out of it, it might not meet the full needs of a product.
Yeah. And I'd throw one other thing out there is that the way that we typically think about materials, and Evan mentioned this at the beginning of the presentation, is as a form of specification. Right? You have a product, you have a vision that you want to bring to life physically, right? And at a certain point, materials come in. And it's not a totally passive thing, and I'm not trying to say that it is, but these materials exist, and they exist before the product, right? And so in the realm of aesthetics, or the visual kind of like unlocks that are now possible, right? Imagine if, right, the material didn't exist before the product. What if the vision for the product actually gave way to the material? And what if the material actually changed the nature of the product of itself, in and of itself? I believe that that's where things are going. We're already sort of here, I mean, you can kind of, we've got printers at the studio, we can print anything we can imagine, right, overnight. I think it's more we need some of the design capabilities in order to actually unlock that creativity within these new kind of technologies. I think aesthetics is going to play a huge role. I also think that the building of brands is going to play a big role, right, in the way that we think about materials moving forward.
Thank you.
Personally, I love the interplay between physicality, physical objects, and Houdini and digital in general. We have some 3D printing fans at Side Effects. Mm-hmm. It's always interesting to see what they come out with.
Absolutely.
So I love all this. Other questions? Yeah.
Hey, so I might have missed, but you said you test for compressibility a lot. What other properties do you test for? Is there like a bunch of more exotic kind of requirements you've ever had, like I don't know, like sound, or I don't know, just trying to think
absolutely,
of some of the more unusual applications for?
Yeah, for sure. We're focusing a bit on the mechanical aspect of metamaterials. There are other types or classes of metamaterials, including acoustic, thermal materials, also materials that work with light in interesting ways in order to visually augment the appearance of things. I've done a lot of work with sound. We're not yet using sound as a driver within the material creation process. However, within the development of visual metamaterials, we have worked on systems where you are using different manufacturing processes, specifically slumped glass, as a way to tune the way that optics are playing through to create vibrancy in a facade of a building. If you've seen the House of Innovation in New York and by Nike, we worked on that facade, and that's a pretty good example of how metamaterials within a visual category can be tuned in order to kind of like unlock new visual characteristics and new visual performance. Yeah, absolutely. One other thing I would just bring up is that although compressibility is important, it's important to remember that you can tune the characteristics through the build. We do a lot of work in footwear, and in footwear you might want to have a moderated forefoot kind of moment. That's very different than how the compression in your heel would manifest, right? You want comfort and sort of resilience in the heel, but you want like robustness and sort of like spring in the forefoot. You can tune the properties of a single material substrate in order to be both, compressive, have compressive characteristics under heel, but also have bending characteristics in forefoot, for instance. So it's not an either or, which is also kind of fascinating. It's like a both and, and in the world of making physical things, that's a pretty unique thing to actually be able to say, oh, I want it to be stiff and flexible, but only in this axis and only when loaded in this criteria. It's kind of interesting, it kind of opens up some new ways to think about, materials and products.
What's the largest object that you've worked on?
Largest object, buildings. So we developed facade systems for a football stadium in Mexico. That's kind of pretty big. But most of our work these days is consumer product, automotive, and medical. A lot of really great medical applications for kind of metamaterial and additive applications, which is pretty exciting.
I could see this for flooring, for example, would be a really nice use case.
Yeah. I mean, anything on or of the building, I think, is up for grabs. Yeah, for sure.
Super cool. Any other questions?
Great talk. Going off of size again, do you ever have any troubles where you need to go super small and then you realize you can't really make anything like that because your printers aren't high fidelity enough?
Yeah, it depends on the technology. So there are certain 3D printing technologies that can print like 9 micron,
Nanoscale.
yeah, nanoscale. So it very much depends on the technology and the application. We haven't run into that limitation yet. And then I guess you can print on nanoscale, but there are constraints in terms of minimum beam dimensions and things like this. So we haven't run into that, but there certainly are some of those limitations. On some of those really high resolution printers, you can't go below 0.2, 0.3 millimeters, 0.5 mil. So that could be a potential limitation.
Yeah, and at the same time, I think that there are new creative ways to interface with these machines as well, right? And we didn't talk about that here, but we're typically familiar with exporting a kind of mesh file, and that file goes to a printer. It somehow gets repaired and gets printed, right? But there are other ways that you can communicate with machines, right? You can really, you can with a voxel kind of describe, layer by layer, exactly what you want that build characteristic to be. And you can now, even with Houdini, we've done this, export image stacks that can be read, as two-dimensional, literally every single layer of a 3D print. And so new modes of communication with machines allow for new ways of thinking about the product. And so when we talk about scale, what is scale when we're talking about the deposition of 80 microns, I guess, it's really, really fine, right? One thing I can't say though is that Houdini hasn't failed us yet when it comes to being able to compute fast, to compute at scale, to compute in a headless state.
And very large data sets.
And very large data sets. And that's been really exciting to see. Coming from a world of CAD, right? Where everything is kind of like an uphill battle when you're talking about building really complex geometry for 3D printing purposes,
Thank you.
Yeah.
I think we at Side Effects all feel like PDG has this really nice opportunity and potential for very interesting use cases, and so it's neat to see it in this case.
Yeah, and maybe as we're transitioning to the next question, I would say that one of the things that's been really exciting is that, and I had an opportunity to speak earlier with some of the wonderful folk from McNeil and Associates. If you guys aren't familiar with Rhino and Grasshopper, talk to these guys because it's good stuff. But Houdini, there's a couple of jumps that typically happen when you're using Houdini, right? You go from working in a parametric software or using some sort of creative coding application, and then you move into this procedural graph and you're like, wait, I start with nodes and I'm not modeling, or whoa, I'm modeling and it's making the nodes. And there's this kind of aha moment where you're like, wow, that's kind of a new thing. And then you go, oh, wait a second, there are these contexts, and you're going like, what do you mean by context? And you realize you're actually not in a modeling tool, but you're actually in a pipeline in this kind of new world, and that gets exciting. And I think the next level with Vex and getting into that, but further down, when you get into PDG and TOPS and all that stuff, there's a really neat moment where you go, well, what about a TOPS first process? What does a TOPS-centric, kind of workflow look like? How do you think creatively about scale at the day one, right? Because everything we do is about scale. If I didn't make that clear, right? We have to make physical things and we got to put millions of them into market. And typically we're working with innovation teams, and typically that process has to happen in 25% of a traditional product development timeline. So everything about what we're doing is impossible, right? So the longer you wait to put a plan in place for scaling an application, the more risk you're introducing into the viability of that particular venture when it needs to scale, right? And PDG and TOPS has been one of those things where I'm like, well, there's the solution. We just start modeling differently to start, and scale comes for free, right? And that's been a real eye-opener. And it has been an enabling technology for us to bring things to bring medical devices to market that are hyper-personalized, going from 3D scan to physical part, all in kind of near real time, and being able to print them without error, but because it's being built fundamentally from this sort of top-centric process. I don't know if anyone asked that question. And if you can't tell, I am a geek. So, all right.
You sort of tiptoed into this area a little bit that I'm about to ask about in your previous answer, but I was wondering, as you're working with clients who, of course, intend to manufacture the products that you're helping them design, have you run into scenarios, or how do you manage when they have kind of well-defined manufacturing constraints to make these medical devices or Nike soles or whatever it may be at a mass scale? Like, how do you bring those limitations or those parameters into your pipeline, or how do you kind of
Yeah, absolutely. It's fundamental to the way that we work. One of the base requirements of bringing any product to market is that you're not going to control the entire supply chain, right? I mean, that's just sort of like, hey, here's the reality of that. And we work very closely to understand what those constraints are, what are the risks involved, what's the tool chain, what are the departments, who owns the data, how's it going to integrate, really kind of all the things that you need to consider. At the end of the day, if we're talking about additive, there are constraints that are more on the side of like the manufacturing process and making sure that whatever you're building is going to be feasible, right? But when we venture into more of the non-additive processes, that's when more conventional methods of make, that's where we get into like really high tolerance requirements and whatnot. Because you're dealing with sometimes Class A surface creation for tooling and whatnot. So it's a balance, right? And I think that it requires a bit of education, because some of the things that seem like, hey, we have to do it this way, it's because you're thinking about the old world and there's this new world. And if you maybe just rejig the way you're thinking about the problem, maybe it's not a problem anymore. And so there's a lot of education that happens. It's referred to as design for additive manufacturing. But you have to educate a little bit the clients on what that means and what are some of the trade-offs. And there's a lot of back and forth, I would say. Yeah, but definitely in the medical space, you're right. There are incredibly stringent requirements that have to be met. And when you're talking about the class of products is called body fitment solutions. So these are solutions that typically go from scan to part. So you create a hyper-personalized fit. In medical, they're sometimes things that can dictate whether or not you may have a malformed body part that could prevent you from ever having like a high quality of life due to a physical element. Getting that right is critical, but doing that in such a way that it conforms to all of the medical standards that are already in place, it's a huge challenge. But that's kind of what makes our day-to-day really cool and fun, because it is a hard problem. These are hard problems to solve.
Because it's mandatory to talk about AI in every conversation. Are you looking at AI in your workflows?
Yeah, absolutely. Yeah. I mean, in very practical ways. I mean, of course, it's funny. So a few answers, right? I kind of use ChatGPT every day, and I use it in the most banal ways possible. And I'm finding that it helps me save time in certain areas, and that's great. So there's like the sort of low-hanging fruit stuff, Mid-Journey and Stable Diffusion, and using some of the great like MLOps stuff. We're using that in Houdini, and we're doing that for our early product concept development. We have a whole kind of workflow built out that's super, super cool using the tools from, the Intagma guys and stuff. And it's amazing. And, it's like we're able to prompt up, and we can take low res models that we sculpt really fast in, Houdini or in Rhino as sub D models, throw them out there and get look dev like, super quick, and things that took us, a week to complete for a deck, might take us an afternoon. And it doesn't mean that we get the time back to go like, kind of mess around or whatever. It just shifts our focus to being able to actually look at these other areas of the problem space that we typically don't get to because we're pushing so hard to hit the deadlines, right? So, and again, that's sort of low-hanging fruit as well. But we have done a lot of work in synthetic data generation. We're starting to build up, massive libraries of data that we're classifying and sort of, looking to segment and sort of build some more intelligence into how our pipeline will be set up. Again, this is more about how we close the loop and actually open up more of a discovery pipeline. That's ultimately the objective of what we're building. And that will require, just a machine learning kind of first sort of mentality in terms of how things will proceed. But that's work we're actively engaged in. Yeah.
Thanks very much, guys.
Yeah,
Excellent.
absolutely. Thank you. Thank you.